The pressure at the bottom of the ocean is over 1,000 times greater than at the surface, enough to crush a human body instantly. And yet, life exists there. Tonight, we'll drift downward far below the surface, descending into the Hadal Zone, where darkness is absolute and pressure is relentless. Along the way, you'll discover how deep the ocean truly goes, what creatures survive there, and why we still know so little about this vast alien world. The deepest point on Earth might surprise you, not just in depth, but in mystery. Before we begin, ask yourself, if more than 80% of the ocean remains unexplored, what secrets might be waiting in the silence below? Chapter 1. Into the Abyss, Mapping the Ocean's Depths. Imagine standing on the deck of a ship in the middle of the Pacific Ocean. The waves rise and fall with gentle rhythm, the surface stretching endlessly in every direction. It's a familiar scene. But just beneath that surface lies an entire world, layered in darkness, pressure, and ancient silence. The ocean is not a single, uniform space. It is structured like an immense vertical cathedral, tiered into zones that grow colder, darker, and more mysterious the deeper one descends. The journey from the surface to the bottom is not just about distance. It is a transition between radically different environments, each with its own rules, challenges, and inhabitants. The first zone is the Pelagic, or sunlight zone, extending from the surface down to about 200 meters. Here, light penetrates freely, supporting photosynthesis and a wide array of marine life. This is the part of the ocean most familiar to us, home to dolphins, coral reefs, and fishing boats. But this layer is only a sliver of the ocean's true depth. Below that lies the Mesopelagic, or twilight zone, ranging from 200 to 1,000 meters. Light fades here into dim blue, too weak for photosynthesis. Many creatures here have evolved large eyes, bioluminescence, or both. It's a transitional layer between the vibrant surface and the realm of the deep. Next is the Pelagic zone, also known as the midnight zone, extending from 1,000 to 4,000 meters. In this region, sunlight disappears entirely. The pressure mounts and temperatures hover near freezing. Most life here is slow-moving, adapted to conserve energy in the absence of light and food. The Abyssopelagic zone comes next, from 4,000 to 6,000 meters. The name comes from the Greek word abyssos, meaning bottomless. The seafloor in many areas lies within this range. Few creatures can survive here. It is a realm of pitch-black, fine sediments and near-total silence. Finally, we reach the Pelagic zone, from 6,000 meters to the deepest parts of the ocean, over 11,000 meters. This is the Hadal Zone, named after Hades, the Greek god of the underworld. It exists only in deep ocean trenches where tectonic plates collide and fold the seafloor into yawning chasms. It is the least explored and most extreme environment on Earth. Mapping the ocean's depths has been a monumental challenge. For much of history, humans had no way of knowing how deep the ocean truly was. The earliest methods were remarkably simple. Weighted ropes dropped over the side of ships. These sounding lines were slow and imprecise, only able to measure depth directly below the ship. In 1875, the HMS Challenger expedition revolutionized our understanding. Using weighted lines and systematic observations, the crew discovered deep trenches and collected thousands of samples from the ocean floor. It was during this voyage that Challenger Deep, the deepest known point in the ocean, was first recorded. But even then, the data was limited to scattered points, like flashlight beams in a vast, dark hole. In the 20th century, echo sounding transformed oceanography. By sending sound pulses from a ship to the seafloor and measuring the time they took to return, scientists could map underwater topography more efficiently. This revealed a dynamic world of underwater mountains, valleys, and plateaus. The mid-ocean ridges, vast underwater mountain chains, were discovered, and with them, key evidence for the theory of plate tectonics. Today, satellite altimetry adds another layer. Though satellites cannot see the seafloor directly, They can detect subtle changes in sea surface height caused by underwater features. A massive underwater mountain, for instance, creates a slight bulge in the water above it due to gravitational pull. By measuring these variations, scientists can infer large-scale structures beneath the waves. Still, more than 80% of the ocean floor remains unmapped in high resolution. That's because the sea is vast, remote, and often inhospitable. Deep sea mapping requires specialized ships, expensive equipment, and time. While we have mapped the surfaces of Mars and the Moon with fine detail, the bottom of our own planet remains elusive. What's down there? We know about vast trenches, some deeper than Mount Everest is tall. We've seen hydrothermal vents spewing mineral-rich water and supporting alien-like ecosystems. We've identified underwater volcanoes, vast sediment plains, and deep scars formed by the slow grinding of tectonic plates. But most of the deep ocean remains unknown, not because we lack interest, but because of how difficult it is to reach. Darkness, distance, and crushing pressure conspire to keep it hidden. The deep ocean does not yield its secrets easily, and yet we continue to try. Each descent into the abyss brings new discoveries, new species, new formations, new questions. The ocean's vertical structure isn't just a physical reality, it's a symbol of how layered and incomplete our knowledge still is. As we move into the next chapter, we'll focus on a place where these depths reach their maximum, the Mariana Trench. What makes this trench the deepest point on Earth? How was it formed? And what exactly lies at its shadowy bottom? Let us descend further. Chapter 2. The Mariana Trench, Earth's deepest place. Picture the tallest mountain on Earth, Mount Everest, standing at over 29,000 feet above sea level. Now imagine submerging that massive peak in the ocean. It would still be swallowed whole by the Mariana Trench. The Mariana Trench lies in the western Pacific Ocean, to the east of the Mariana Islands. It is not a narrow crack, but a long crescent-shaped scar in the Earth's crust, stretching over 1,500 miles. At its deepest point, Challenger Deep, the seafloor drops to nearly 36,000 feet below sea level. That's deeper than commercial airliners cruise above the ground. But how did this extraordinary trench come to be? The Earth's surface is not a solid shell, but a dynamic crust made of massive plates that drift slowly over time. Where these tectonic plates meet, the Earth reshapes itself. The Mariana Trench is the result of one such meeting between the Pacific Plate and the smaller Mariana Plate. As the Pacific Plate pushes westward, it is forced underneath the Mariana Plate in a process known as subduction. This constant geological movement drags the ocean floor down into the Earth's mantle, forming a trench as deep as any on the planet. The trench isn't uniform in shape. Its floor is uneven, a jagged mix of slopes, sediment, and faults. Within this submerged chasm lies the Challenger Deep, the single deepest known point in the ocean. It was named after the HMS Challenger, the British ship that first measured its depth in 1875 using a simple weighted rope. At that time, they estimated a depth of over 8,000 meters. Later measurements, using echo sounders and sonar, confirmed and refined the numbers. The most precise measurement currently puts Challenger Deep at about 10,935 meters, or 35,876 feet. By comparison, if Mount Everest were placed at the bottom of the trench, its peak would still be submerged by over 1.2 miles of water. Despite its fame, the trench is among the least explored places on Earth. The crushing pressure at the bottom, over 1,000 times the atmospheric pressure at sea level, makes it incredibly difficult to reach. Any object or vessel descending into these depths must withstand pressure equivalent to 8 tons per square inch. The first successful manned descent into Challenger Deep was made in 1960 by Jacques Piccard and Don Walsh aboard the Bathyscaphe Trieste. Their tiny, pressure-resistant sphere took nearly 5 hours to reach the bottom. Once there, they spent just 20 minutes before ascending. Due to the sediment stirred up by their landing, they saw little, just a glimpse of flat, featureless bottom and one small fish, possibly misidentified in hindsight. It would be more than 50 years before another human visited Challenger Deep. In 2012, filmmaker and explorer James Cameron made a solo descent in a custom-designed submersible called X-Deep-Sea Challenger. His dive marked a new era in deep-sea exploration, capturing high-definition footage and collecting samples for scientific analysis. Cameron described the bottom as desolate, lunar, and greenish in hue, covered in fine silt and populated with tiny shrimp-like creatures. More recently, unmanned robotic vehicles have begun exploring the trench with greater precision. These remotely operated vehicles, ROVs, and autonomous underwater vehicles are designed to endure the crushing depths for extended periods. Some are equipped with high-resolution cameras, manipulator arms, and instruments to sample water, sediment, and microbial life. And yes, there is life down there. Even in the trench's deepest recesses, researchers have discovered resilient microorganisms thriving under pressure and cold. These extremophiles feed on chemicals in the water, surviving in an environment that lacks sunlight entirely. Their discovery has challenged previous assumptions about the limits of life on Earth. But exploration has also revealed something more troubling: pollution. In 2018, scientists found plastic debris, likely a shopping bag, at the bottom of the Mariana Trench. Microplastics have also been detected in sediment samples. These findings highlight a sobering truth: human impact reaches even the most remote corners of the planet. Geologically, the trench is also a site of complex processes. Subduction zones like this one are responsible for some of the most powerful earthquakes and volcanic activity on Earth. As the Pacific plate is pushed downward, it melts and causes magma to rise, fueling the volcanic activity of the Mariana Islands and nearby underwater volcanoes. Sediment layers in the trench preserve a quiet record of time. Tiny particles of dust and organic matter slowly sinking to the bottom, forming a layered archive of the planet's past. By analyzing core samples from these sediments, scientists can study climate patterns, historical extinction events, and even the chemistry of ancient oceans. The Mariana Trench is not just a geographical feature, it is a frontier, a place where Earth hides its deepest secrets. It reminds us how much of our planet is still shrouded in mystery. While satellites orbit distant planets, parts of our own world remain nearly untouched, their stories waiting in the cold, dark silence of the deep. In the next chapter, we'll explore the forces at work in these crushing depths. What exactly happens to matter and life under such extreme pressure? And how does the absence of light shape everything that dwells there? Let's continue our descent. Chapter 3: Life in the Darkness, Creatures of the Deep. Imagine a world without sunlight, not a cloudy day or a moonless night, but complete, eternal darkness. A place where the sun's rays have never reached. This is the environment of the deep ocean, where life has evolved under immense pressure, near freezing temperatures, and in the absence of light. And yet, against all odds, it is not a lifeless void. The creatures of the deep are some of the most extraordinary forms of life on Earth. They have adapted to conditions that would crush, freeze, or starve most surface-dwelling organisms. Their adaptations are not just bizarre, they are elegant solutions to a harsh, unforgiving world. One of the most striking features of deep-sea life is bioluminescence. In the absence of sunlight, many organisms generate their own light. Tiny chemical reactions within their bodies produce a soft, cold glow. Blue, green, sometimes red. This light can be used to attract prey, evade predators, or communicate in the dark. The anglerfish is perhaps the most iconic bioluminescent predator. The female, which can grow much larger than the male, has a glowing lure that extends from her forehead, a fleshy filament tipped with a bulb of light-producing bacteria. She floats motionless, waiting in the dark. When a smaller fish is drawn toward the light, mistaking it for prey, she strikes with lightning speed. But anglerfish are only one example. There are jellyfish that pulse with colored lights, squid that eject glowing clouds to distract predators, and tiny copepods that flash to warn others of danger. In a world where eyes must be enormous and finely tuned, light becomes both weapon and signal. Other creatures rely on stealth and camouflage. The gulper eel, with its massive mouth and tiny body, can swallow prey much larger than itself. The vampire squid is not truly vampiric, but its cloak-like arms and deep red color help it blend into the dark. It also produces bioluminescent displays, though not to hunt, only to startle and escape. Food is scarce in the deep ocean. Without sunlight, there are no plants and thus no photosynthesis. Most life depends on marine snow, a slow rain of organic debris drifting down from the surface. Dead plankton, fecal matter, and bits of decaying organisms settle gently through the water column, providing vital nutrients to life below. In some places, however, entirely different food chains have emerged. Around hydrothermal vents, cracks in the sea floor where hot, mineral-rich water gushes out, unique ecosystems flourish. These vents, discovered only in the late 1970s, support communities based not on sunlight but on chemosynthesis. Here, bacteria convert chemicals like hydrogen sulfide into energy, forming the base of a food web unlike any other on Earth. Giant tube worms, often over 6 feet long, cluster near these vents. They have no mouths or digestive systems. Instead, they rely on symbiotic bacteria living inside their bodies to produce energy. Other vent dwellers include white crabs, blind shrimp, and unusual clams, species found nowhere else. In the deepest parts of the ocean, like the Hadal zone of trenches, life persists in astonishing forms. Small amphipods, shrimp-like scavengers, feed on whatever organic material reaches these depths. Some species have developed enzymes and proteins uniquely resistant to pressure, allowing their cells to function in conditions that would rupture others. Microbial life thrives in the sediment and water of the trench floors. These tiny organisms may hold clues to the origin of life on Earth, and possibly life beyond it. Their ability to survive without sunlight, under crushing pressure and near zero temperatures, makes them a focus for researchers studying potential life on icy moons like Europa or Enceladus. And yet, for all we've discovered, the deep sea remains largely unknown. It's estimated that as much as 90% of deep-sea species are still undescribed. Each expedition brings new findings: jellyfish with never-before-seen structures, fish that walk along the seafloor, and microorganisms with novel genetic signatures. Studying these organisms is not easy. Bringing them to the surface often damages their fragile bodies. Specialized pressure-retaining containers are needed to keep them alive for study. Even then, much of what we learn comes from remote cameras and deep-diving robots that record their behavior in situ. There is a quiet grace to these life forms. They do not rush, they do not dazzle with color or sound. Instead, they move slowly, deliberately, shaped by millennia of adaptation to a realm few will ever see. Their existence challenges our assumptions about what life requires. They live not in spite of the darkness, but because of it. In the next chapter, we'll turn our attention to the physical conditions that define the deep ocean. What does extreme pressure do to matter? How do temperature and salinity change with depth? And how do these forces influence everything that exists in the abyss? Let us sink even deeper. Chapter 4: Pressure, Cold, and Silence. The physical extremes of the deep. At the ocean's surface, life feels familiar. The air is warm, pressure is gentle, and light stretches far in every direction. But as you descend into the depths, each of these comforts begins to fade. 1,000 feet below, sunlight weakens. At 2,000, the blue begins to vanish. And beyond that, into the abyssal and Hadal zones. The ocean becomes a place governed not by sight or sound, but by silence, cold, and immense pressure. Let's begin with pressure. At sea level, we live under 1 atmosphere of pressure, roughly 14.7 pounds per square inch. This is the weight of Earth's atmosphere pushing down on us, though we hardly feel it. But for every 10 meters, about 33 feet, you descend in the ocean, pressure increases by 1 additional atmosphere. By the time you reach the depths of the Mariana Trench, more than 1,000 times that pressure bears down on every square inch of surface. This force is almost unimaginable. At the deepest point, around 36,000 feet, the pressure exceeds 16,000 pounds per square inch. That's equivalent to the weight of 100 adult elephants pressing on an area the size of a postage stamp. For comparison, the pressure in a car tire is about 30 psi. At those crushing depths, unprotected objects collapse like paper cups. And yet, life finds a way to exist. Organisms living in the Hadal zone have adapted at the cellular level. Their membranes contain unique lipids that remain fluid under extreme pressure. Their enzymes are pressure-tolerant, allowing basic metabolic processes to continue. Proteins inside their cells are folded in stable configurations, resistant to being denatured. Even the physical structure of deep-sea organisms is adapted to the pressure. Many have soft, gelatinous bodies that do not rely on internal air spaces, which would be crushed. Instead of lungs or swim bladders, they may rely on oil-filled sacs or simply live in constant, slow suspension. The pressure doesn't just affect living things, it alters the behavior of matter itself. Water at extreme depths behaves differently than at the surface. It becomes denser, less compressible, and even affects the solubility of gases. Sound travels faster and farther, but not in familiar ways. It bends and refracts in layers, sometimes creating distant echoes or strange underwater illusions. Then there's the cold. Beyond the sunlit surface, temperatures drop sharply. At depths of a few hundred meters, the ocean enters what is called the thermocline, a region where temperature plummets rapidly. Below that, in the deep ocean, temperatures stabilize just above freezing, often between 0 and 4 degrees Celsius, 32–39 degrees 1. This unrelenting cold slows metabolic rates. Life in the deep tends to move slowly, grow slowly, and reproduce at a glacial pace. Deep-sea fish may live for decades or even centuries. The Greenland shark, found in cold northern waters, is thought to live for over 400 years, though it dwells at shallower depths than the Hadal zone. The low temperatures also affect chemistry. Reactions proceed more slowly. Decay is inhibited. Organic material can persist on the seafloor for astonishing lengths of time, preserved by the cold, dark stillness. It's a kind of natural refrigeration that delays decomposition and keeps ancient sediments intact. Now consider the silence. The deep ocean is not merely dark and cold, it is also profoundly quiet. Above, in shallower waters, waves crash, boats hum, whales call. But in the Hadal depths, all of that noise fades away. What remains is a subdued world where the loudest sound may be the shifting of rock, the settling of sediment, or the occasional rumble of a distant earthquake. And yet, the silence is not absolute. Some deep-sea creatures make sound clicks, pulses, or faint rhythmic vibrations. These noises are often used for communication, navigation, or territorial displays. But they are subtle, infrequent, and rarely heard by human ears. The ocean depths are more whisper than roar. Human-made noise, however, is beginning to intrude. Submarines, seismic surveys, and shipping traffic all send vibrations through the water. Some of these sounds reach even the deepest trenches, raising concerns about their effects on marine life that evolved in near-total silence. Temperature, pressure, and sound all shape the physical environment of the deep ocean, but they also shape the behavior of explorers. Submersibles must be engineered to withstand incredible forces. Their hulls are spherical, the strongest geometric shape for withstanding pressure, and often made of titanium or special composite materials. Every bolt, seam, and cable must be tested and retested. One failure can be catastrophic at such depths. Deep-sea exploration also demands careful attention to temperature control. Electronics must be insulated. Fluids must be managed so they don't freeze or contract. Every sensor, motor, and camera must be able to perform in near-zero temperatures for hours or even days at a time. Despite the challenges, technological progress continues. Robotic explorers now reach places that were once beyond imagination. They map the terrain, record the sounds, and analyze the chemistry of the abyss. With every dive, we learn more about the strange and silent physics of the deep. It's humbling to realize that we live on a planet where the most extreme environments are not found on mountaintops or in distant deserts, but beneath our own oceans. These places are not hostile in the way a storm or wildfire is. Rather, they are indifferent, vast, unchanging, and immense. In the next chapter, we will explore how the deep ocean connects to the surface world. From carbon cycles to climate regulation, from deep currents to global heat distribution, this hidden world exerts a quiet but powerful influence on the planet we call home. Chapter 5: The History of Deep-Sea Exploration. In the year 1872, a converted British warship set sail from Portsmouth Harbour, loaded not with cannons, but with microscopes, dredging nets, sounding lines, and a small army of scientists. This was the HMS Challenger, and its 4-year voyage would mark the beginning of modern oceanography. Before it, the deep ocean was more mystery than map, spoken of in myths, feared as a bottomless pit, and studied only from the safety of the shore. Yet even before the Saganger expedition, curiosity about the deep ocean ran deep in the human story. For centuries, sailors speculated about what lay beneath the waves. Ancient cultures saw the sea as a realm of gods and monsters. The Greeks imagined giant squids and sea serpents. Medieval maps labeled uncharted waters with Latin warnings. Hic sunt draconesque, here be dragons. The ocean floor was thought to be flat, lifeless, and eternally still. In truth, no one knew. The technology simply did not exist. The earliest real glimpses came not from direct observation, but from weighted ropes. For hundreds of years, mariners used sounding lines, long cords with lead weights to measure depth. But these could only reach a few hundred meters before becoming impractical. Anything deeper remained inaccessible, a mystery wrapped in pressure and darkness. That began to change in the 19th century. In 1840, the British ship HMS Erebus conducted some of the first systematic depth measurements in the South Atlantic. A few decades later, the Challenger's expedition revolutionized ocean science. During its voyage from 1872 to 1876, the Challenger crisscrossed the globe, collecting samples of seawater, sediments, and marine life. It measured ocean temperatures and depths at hundreds of locations. Using heavy rope and iron weights, it recorded a sounding of over 8,000 meters in the Mariana Trench, a depth so staggering that many scientists doubted the reading at the time. More importantly, the Challenger proved that life existed in the deep. The team dredged up hundreds of new species from abyssal depths, starfish, mollusks, brittle corals, disproving the prevailing belief that the deep sea was sterile. It showed that the ocean was not a dead zone, but a vibrant alien world waiting to be explored. In the decades that followed, progress was slow but steady. Advances in diving suits and deep-sea nets allowed for more extensive sampling. By the early 20th century, powered winches and steel cables replaced hemp ropes, enabling greater accuracy and depth. Then, in the 1930s, a pair of pioneers changed everything. William Beebe, an American naturalist, and Otis Barton, an engineer, descended into the deep ocean in a steel sphere called the bathysphere. Suspended from a cable and equipped with a small window, the bathysphere allowed them to observe life directly at depths of over 3,000 feet, far beyond the reach of divers. Beebe described glowing jellyfish, strange fish with tubular eyes, and eerie, silent darkness. Though limited by technology, their dives marked the first human glimpses into the deep from within. But cables had their limits. To go deeper, explorers needed self-contained submersibles. Enter the bathyscaphe. In 1960, Swiss engineer Jacques Piccard and U.S. Navy Lieutenant Don Walsh climbed into the AT Trieste, a specially designed deep-diving craft. Beneath them lay the Mariana Trench, specifically the Challenger Deep, the lowest known point on Earth's surface. The Trieste Eck was unlike anything before it. Its pressure sphere, made of thick steel, hung below a massive float filled with gasoline, chosen for its incompressibility. As the vessel sank, the outside pressure rose to over 16,000 psi. Inside, Piccard and Walsh sat in silence, surrounded by nothing but darkness and the occasional sound of the hull creaking under stress. After nearly 5 hours of descent, they touched the seafloor, 10,911 meters, 35,797 feet beneath the waves. What they saw surprised them. Silt billowed from the bottom, stirred by their arrival, and then a fish, possibly a flatfish, glided past their viewport. Life, it seemed, was possible even here, in the most remote part of the planet. After only 20 minutes, they began their ascent. No photographs were taken, and no samples were collected. But the AT Trieste's dive proved that humans could reach the deepest ocean and return. In the years that followed, deep-sea exploration shifted from daring manned missions to remote-controlled vehicles. ROVs, or remotely operated vehicles, became the workhorses of ocean science. Equipped with cameras, robotic arms, and scientific instruments, they could reach depths too dangerous for humans and stay for hours at a time. One of the most advanced ROVs, Jason, operated by the Woods Hole Oceanographic Institution, has explored hydrothermal vents, shipwrecks, and trench floors. Its sibling, Narrated, reached the bottom of the Mariana Trench in 2009, one of the few vehicles to do so. Sadly, it was lost during a later mission, a reminder of how treacherous deep-sea exploration remains. But curiosity persists. In 2012, film director James Cameron piloted a one-man submersible to the Challenger Deep, becoming the first person to make a solo dive to Earth's lowest point. His mission, part science and part personal quest, brought high-definition cameras and scientific tools to a place that had not been visited in over 50 years. In recent years, private ventures have joined the effort. Victor Vescovo, aboard the SDSV Limiting Factor, conducted a series of record-breaking dives, visiting the deepest points of all 5 oceans. These expeditions have uncovered new species, mapped previously unseen seafloor, and demonstrated that even the most inaccessible parts of the planet can be explored with the right technology. The history of deep-sea exploration is still unfolding. With each mission, new questions arise. What unknown organisms lie beneath the sediments? How do trench ecosystems function? Can these depths reveal clues about Earth's climate history, or even the possibility of life elsewhere in the universe? It is a story marked by patience, innovation, and persistence. A story where each chapter is written slowly, in the language of pressure and silence. In the next chapter, we'll turn our attention to what the deep ocean means for life above it. From climate regulation to carbon capture, this hidden realm plays a quiet yet crucial role in shaping the world we live in. Chapter 6: Why So Much Remains Unknown. Imagine standing at the edge of a vast, unfamiliar forest. One that stretches farther than any mountain range, plunges deeper than any canyon, and covers nearly 3/4 of the Earth's surface. Now imagine that despite centuries of effort, you've only explored a narrow trail just inside the tree line. That is our relationship with the ocean, and especially the deep ocean. Though we've sent satellites to the far reaches of our solar system and rovers to the surface of Mars, more than 80% of our own ocean remains unexplored. The seafloor, vast and ancient, hides beneath miles of water, inaccessible to all but the most sophisticated tools. Even today, we have mapped only a fraction of the deep sea in high resolution. In many ways, the deep ocean is Earth's final frontier. But why? Why does so much remain unknown about something so near just below our feet? The answers lie in a combination of technical challenges, logistical barriers, and scientific limitations, all woven into a quiet, ongoing story of exploration. The first and most obvious challenge is depth. Water is heavy. Every additional meter increases pressure. At the deepest points in the ocean, that pressure becomes immense, over 1,000 times greater than what we experience at sea level. Most machines, and certainly most living things, cannot survive such crushing forces. Building equipment that can endure it requires specialized materials, precise engineering, and rigorous testing. Every submersible, every probe, every sensor must be designed to withstand this pressure for hours or even days. This makes exploration slow and expensive. Unlike satellites, which can orbit the entire globe in hours, deep-sea vehicles move at a crawl. A single descent can take hours just to reach the bottom, and the area explored in a single dive is minuscule. Mapping even a small region at high resolution may take weeks or months of repeated visits. And unlike exploring a desert or forest, there's no easy way to simply walk around and look. Another major challenge is communication. Radio waves, which enable GPS, Wi-Fi, and most modern communication technologies, do not travel well through seawater. They're absorbed almost immediately. Instead, deep-sea vehicles must use acoustic signals, slow, low bandwidth, and prone to distortion. This means real-time communication is limited. Remote-operated vehicles must rely on tethered cables, and autonomous vehicles must work largely on their own. It's like trying to explore a foreign land through a thick fog, using only a walkie-talkie with a long delay. Then there's visibility. The deep ocean is completely dark. Sunlight disappears by about 1,000 meters, and beyond that, the world is cloaked in perpetual night. Lights can be used, but they reach only a few feet in front of a camera lens. Sediment easily stirred from the seafloor can cloud visibility further, creating an impenetrable murk. Even when conditions are ideal, the visual field is narrow, like looking through a keyhole into an endless hallway. This limits what can be seen, photographed, or studied in a single mission. Even when samples are collected, organisms, sediments, fluids, they often change once brought to the surface. Creatures adapted to intense pressure and cold can be damaged or killed during ascent. Their bodies may collapse. Gases trapped in their tissues expand. Many never survive the journey. As a result, what we know of deep-sea life is often based on incomplete observations or brief, unrepeatable encounters. There are also environmental reasons why we know so little. The deep ocean is vast and variable. Some regions are smooth plains, others are jagged ridges or trench walls. Volcanic vents, methane seeps, and landslides create constantly changing landscapes. Life in one trench may be dramatically different from that in another. No single expedition can hope to capture the full diversity of these ecosystems. Even after decades of study, every new dive reveals something unfamiliar, a species, a behavior, a chemical process. And then there is the matter of funding. Ocean exploration is expensive. Unlike space exploration, which often captures the public imagination, deep-sea research is quiet, slow, and difficult to visualize. It lacks the dramatic visuals of rockets and planets. Budgets are often limited, and priorities shift. Many missions are conducted by universities or non-profits, relying on grants or partnerships. Despite its importance to Earth's climate, biodiversity, and resources, the deep ocean often receives less attention than it deserves. This slow pace also reflects a lack of coordination. Because the ocean spans the globe, many countries share jurisdiction over different parts of it. Research is often siloed, conducted in isolation, with different standards, tools, and goals. Data from one expedition might not be compatible with another. Collaboration is improving, but there is no single global effort to map or understand the deep sea in its entirety. Even now, entire mountain ranges lie hidden beneath the surface. Vast plains stretch uncharted, trenches plunge into darkness that no light has ever touched. And in these places, life thrives, life that may hold answers to some of our biggest scientific questions. How did life begin? Could similar organisms exist on icy moons like Europa or Enceladus? What secrets lie buried in the sediments? Records of past climates, extinctions, or tectonic shifts? Could new medicines, enzymes, or materials be waiting to be discovered in the bodies of strange deep-sea creatures? Each of these questions points to a simple truth: we don't yet know what we don't know. But even within that uncertainty, progress continues. New mapping initiatives are underway, using sonar-equipped drones and satellites to chart the seafloor. Advances in artificial intelligence are helping scientists analyze complex datasets from remote regions. Portable labs are making it easier to process samples on board ships. And as technology becomes more affordable, more eyes are turning toward the deep. Curiosity is resilient. The deep ocean may remain largely unknown, but it is not unknowable. Every dive adds a brushstroke to the canvas. Every sensor, every sample, every photograph brings a small corner of that vast darkness into view. It may take decades or centuries, but the ocean is slowly giving up its secrets. In the next chapter, we'll explore what scientists have found so far. From hydrothermal vents to bioluminescent creatures, from ancient fossils to strange new forms of life, we'll look at the remarkable discoveries that have reshaped our understanding of what the deep ocean really is. Chapter 7: The Deep Sea and the Origins of Life. Picture the seafloor, far below sunlight's reach, where darkness is endless and pressure immense. The water is near freezing, silence dominates, but here, in this quiet void, something remarkable happens. A fissure in the Earth's crust begins to vent mineral-rich fluid into the surrounding water, hot, chemical-laden, and brimming with possibility. Around it, life gathers. This is a hydrothermal vent, and for many scientists it represents one of the most compelling clues about where life on Earth may have begun. Traditionally, the origin of life was thought to lie in shallow waters, perhaps a warm little pond, bathed in sunlight and fed by simple molecules. But discoveries made in the deep sea over the past few decades have shifted that thinking. The idea that life could emerge and even thrive in total darkness, powered not by sunlight but by chemistry, has profoundly changed our understanding of life's earliest beginnings. In 1977, a team of researchers exploring the Galapagos Rift stumbled upon something no one had predicted. Using a deep-sea submersible, they discovered hydrothermal vents surrounded by dense clusters of previously unknown organisms: tubeworms, giant clams, strange crabs, and more. What astonished them wasn't just the diversity, but the fact that these ecosystems were completely independent of sunlight. Instead of photosynthesis, they were powered by a process called chemosynthesis. In chemosynthesis, microorganisms convert chemical energy, often from hydrogen sulfide or methane, into food. These microbes form the base of the food web, supporting entire communities of animals. In other words, life at these depths had found a completely separate energy source, and it had done so in some of the harshest conditions on Earth. The implications were profound. If life could exist in such a place, perhaps it could also originate there. Hydrothermal vents offer several features that make them attractive candidates for the origin of life. First, they provide a steady supply of heat and minerals, key ingredients for biochemical reactions. The steep chemical gradients between the hot venting fluids and the cold surrounding seawater could have created the right conditions for complex molecules to form. Second, these vents are rich in metals like iron and nickel, which can act as natural catalysts. In controlled experiments, scientists have shown that these metals can help assemble simple molecules into more complex chains: amino acids, nucleotides, and even the building blocks of RNA. Third, Some types of hydrothermal vents, called alkaline vents, have porous structures made of mineral chimneys. These porous networks may have served as natural reactors, tiny chambers that concentrate molecules and provide shelter from the harsh environment. In these microenvironments, primitive biochemical processes could have taken their first steps. Some researchers propose that early forms of RNA, an essential molecule for life, could have formed within these mineral pockets. Over time, these molecules might have evolved the ability to replicate, metabolize, and eventually give rise to cellular life. The deep sea, then, is not just a place where life survives, it may be where life began. But the story doesn't stop there. The study of these deep sea environments also has implications far beyond Earth. If life can exist in darkness, using chemistry alone, then similar ecosystems might exist elsewhere in our solar system. Moons like Europa and Enceladus, with their subsurface oceans and possible hydrothermal activity, suddenly seem less alien. Missions to explore these worlds often look to Earth's deep ocean as a blueprint. In fact, some of the same types of microbes found near Earth's hydrothermal vents could theoretically survive on other worlds. Their ability to live without light, in high pressure and with limited resources, makes them excellent candidates for studying potential extraterrestrial life. Back on Earth, the deep sea continues to offer surprises. Scientists have found organisms that use entirely novel metabolic pathways. Some bacteria feed on methane, while others digest rock. Certain archaea primitive microbes that resemble ancient life can survive in boiling water, extreme acidity, or complete isolation from surface ecosystems. Each new discovery adds a piece to the puzzle of life's origin. Some researchers now believe that life may not have started just once. It's possible that life tried and failed many times in different environments, shallow pools, clay beds, icy comets, before finally taking hold in the deep sea. Even if hydrothermal vents weren't the original birthplace of life, they may have served as a safe haven for early organisms, a place to evolve complexity while the surface of the Earth was still unstable and hostile. In this way, the deep sea becomes both cradle and sanctuary, helping life not just to begin, but to persist. There's also the matter of time. The ocean has existed for over 3.8 billion years. For most of that time, life was microbial. Complex organisms like animals and plants are relatively recent developments. The deep sea holds sediments and rock formations that have been undisturbed for eons. Within them may lie preserved chemical signatures or fossilized remains of life's earliest stages. By drilling into these deposits, or sampling vent fluids, scientists hope to uncover clues about how life transformed from simple molecules into the diversity we see today. But much remains unknown. Despite decades of research, we still don't fully understand how life made the leap from chemistry to biology. The transition from non-living matter to a self-replicating system is one of the most profound mysteries in science. And the deep ocean, with all its isolation and resilience, remains one of the best places to look for answers. In many ways, the deep sea is like a time capsule, preserving conditions similar to those on early Earth. Its ecosystems are slow to change, untouched by surface weather, and resilient to extinction events. They may offer insights not only into the origin of life, but also into how life might continue in the future, long after surface conditions have changed. In the final chapter, we'll step back and reflect on what the deep ocean means, not just scientifically, but philosophically. In a world so focused on speed, light, and immediacy, the deep sea offers a different kind of perspective, one of patience, mystery, and quiet endurance. Chapter 8. The Ocean Within Us. Drift gently back in time billions of years, before the first vertebrates crawled onto land, before trees rooted into soil, before even the simplest fish flicked through the waves. Earth was a water world, and from that water, life emerged. And though we now walk on land, breathe air, and look up at stars, the truth remains: we are still creatures of the sea. The ocean is not only around us, it is within us. Our bodies, though seemingly distant from that alien deep, carry echoes of its chemistry. The salt in our blood mirrors the salinity of ancient seas. The water in our cells, structured and balanced so precisely, bears the signature of an oceanic past. Our nerves fire with electrical impulses not unlike those used by deep-sea creatures to communicate in the dark. Our organs function with minerals and compounds that first evolved in waterborne life. In fact, the embryo of a human being develops in a warm, fluid environment not unlike a tiny sea. For weeks, the developing fetus even carries structures that resemble gills, vestiges of a long evolutionary journey from fish to mammal. The language of our biology speaks fluent ocean. Even more subtly, the rhythms of the sea linger in us. The tides, governed by the moon, find echoes in our circadian rhythms, in the monthly cycles of biology, and perhaps in the deep psychological draw we feel toward water. The sound of waves, the scent of brine, the sight of shifting light on its surface, all evoke something primal, something remembered. Yet, for all the familiarity we feel with the ocean, the deeper layers remain unknowable to most. The abyssal plains, the trenches, the hydrothermal vents. These are worlds apart, operating on scales of pressure, time, and temperature that strain the imagination. And yet, they too are part of the same Earth we inhabit. The deep sea is not some separate realm, but an extension of our own biosphere. And within that extension lies a different kind of life, one that is older, quieter, more patient. There, life does not hurry. A fish may live for a century without seeing the surface. A colony of deep-sea corals may have begun growing before the first human civilization rose. The deep sea moves slowly, breathes slowly, changes slowly, and in that slowness there is wisdom. It reminds us that not all things are revealed at once. In a culture obsessed with light and speed, the deep ocean teaches a different lesson. That mystery is not the absence of knowledge, but the presence of something waiting to be understood. It invites stillness, it invites wonder, and perhaps most importantly, it invites humility. Because even now, with all our technology and ambition, we have barely begun to grasp the deep sea's full story. We know that it plays a vital role in regulating our planet's climate, that it stores vast amounts of carbon, moderates temperature, and shapes weather patterns. We know that its currents move like invisible rivers beneath the surface, connecting continents and carrying nutrients. We know that its organisms, many still undiscovered, may hold answers to questions in medicine, energy, and biotechnology. But we also know that the more we explore, the more complex the picture becomes. In each dive, each sample, each new species, we find not closure, but continuation. The ocean does not yield its secrets easily. It offers them slowly, like pages from a long-forgotten book. And that may be its greatest gift. Because in seeking to understand the deep sea, we are not just learning about water, pressure, or strange organisms. We are learning about life itself, its resilience, its creativity, its ability to adapt, evolve, and survive in the most unexpected ways. And we are reminded that we too are part of that story. From the first spark of life near a hydrothermal vent to the quiet breath of a person falling asleep beside the sea, the connection endures. The ocean flows not just across the surface of our planet, but through our veins, through our history, and through our imagination. In the silence of the deep, in the cold and the dark, life continues slowly, patiently, without need for applause. And in that deep, perhaps, we find not only the origin of life, but something even more profound, a mirror. One that shows us how little we truly know, and how beautiful that mystery can be. So as you rest, as your breath slows and your thoughts begin to drift, remember this: the ocean never sleeps. It waits, it listens. And somewhere, in that quiet vastness, the story of life continues to unfold, one gentle current at a time.